Welcome everyone. Today we have Bernd Sturmfels as our SIAM SAGA speaker, and Bernd is director at the Max Planck Institute for Math and the Sciences in Leipzig, and professor at UC Berkeley, and honorary professor at the University of Leipzig and TU Berlin, and is going to tell us about linear spaces of symmetric matrices.
Yeah, thank you very much for the invitation. It's a great pleasure to speak here. So I'd like to tell you about LSSM. So you see in green the logo, linear spaces of symmetric matrices. And in particular, I will explain what the logo means, what the picture means, and what the triangle of numbers means. So the setting is, we're looking at the space Sn of real symmetric n by n matrices. So this is a real vector space of dimension n+1 choose 2. And inside this vector space, we have a open cone, the cone of positive semi-definite matrices. So a miracle of math, a miracle of linear algebra is that the n by n real symmetric matrix has all eigenvalues real, the spectral theorem. And if those eigenvalues are all positive, then we say the matrix is positive definite, and the set of such matrices forms a convex cone, non-polyhedral cone. It's semi-algebraic. It's defined also by polynomial inequalities, namely the positivity of the principal minors. Suppose L is a linear subspace of dimension m inside our n+1 choose 2 dimensional space of matrices. And let's also assume that it has a non-empty intersection with our cone. Well, then the intersection is a convex cone of dimension m. So we're going to be interested in such intersections. Now, to draw a convex cone of dimension m, we can gain one dimension by slicing the cone with an affine hyperplane, and this gives us a convex body of dimension m-1. So here's a cartoon. This picture shows the situation for n equals 3 and m equals 4. So our cone lives in the 6th-dimensional space of symmetric 3 by 3 matrices. We're slicing it with a 4-dimensional plane. Then we get a 4-dimensional convex cone, and then that's the cone over a 3-dimensional yellow convex body. So this yellow convex body is shown here. It looks like a samosa, what you eat in an Indian restaurant, or a puffed up tetrahedron. So imagine taking a tetrahedron and blowing some air into it. You get a convex body that retains the 6 edges connecting any 2 vertices of the tetrahedron, but the triangular faces are rounded out. They're made fat. Now, the boundary, the yellow boundary of this convex body is a cubic surface defined by the vanishing of the 3 by 3 determinant. And that cubic surface has more points. There are these red elephant ears that go off towards infinity. And here in the diagram, inside the yellow body, the 3 eigenvalues are positive. On the yellow boundary, 2 positive eigenvalues, 1, 0. Then outside, 1 negative eigenvalue, then you transition, and then the interior of the elephant ears, we would have 2 negative eigenvalues, 1 positive eigenvalue for our 3 by 3 matrix. Now, these objects, these intersections in the optimization literature are known as spectrahedra, and in statistics, they arise as linear Gaussian models. And I like to talk about those 2 settings a little bit because optimization and statistics are, of course, foundational for data science, and data science is what everybody does these days. So here are 2 optimization problems that are related to our situation. So let's look at our spectrahedron. I now take the cone, I close it up, and I intersect it with a affine linear space. So now I have the closed yellow convex body, and semi-definite programming is the optimization problem of minimizing a linear function over this spectrahedron. Now in the space of matrices, it's customary to write linear functionals by the trace inner product. So you give me a square matrix S. I take the matrix product. Then I take the trace of that matrix product, the sum of the diagonal entries. That's a linear form on the space of symmetric matrices, and every linear form comes this way. So that's our first optimization problem called semi-definite programming. A second optimization problem is maximum likelihood estimation. And this is what the way we set this up here is we look at the open spectrahedral cone, and we're minimizing the so-called log likelihood function. So this is the logarithm of the determinant of x. So since x is in the positive definite cone, the interior, the determinant is a positive real number. The logarithm of a positive real number is well defined, and then we now subtract the trace inner product. So that's also a perfectly good function, and maximum likelihood estimation in this setting, we're interested in maximizing this function. The two pictures just give a little bit of context. So here's an example of a spectrahedron arising from 3 points in the plane. And then, of course, Gaussian models play a huge role in data science and clustering. So here's a clustering picture. Now, is this data science or is it actually algebraic geometry? Well, maybe it's both. So what is algebraic geometry? So in algebraic geometry, we might ask questions about m equals 2 quadrics in the plane. So the plane for us here is the projective plane, or in 3 space, which here is the 3-dimensional projective space. So we're identifying symmetric matrices with quadrics, quadratic hypersurfaces. So here, this picture of a blue circle and a green ellipse in the plane really is the picture of 2 symmetric 3x3 matrices. So symmetric 3x3 matrices define quadratic forms in 3 variables and hence conics in the plane. Now, what can we say about 2 conics in the plane? Well, what we can say is that they always meet in 4 points, in 4 red points. That's Bézout's theorem. Now, those 4 points can all be real, as it is here, but it could also happen that these red points become imaginary. So for example, if you slide the green ellipse to the right, then the 2 red points travel closer and closer to each other, and then poof, they become a complex conjugate pair. If we slide the ellipse further to the right all the way, then there are no more red real intersection points, but all 4 intersection points are complex. In any case, they're always counting multiplicity 4 intersections for 2 conics in the plane. Now, if I take 2 symmetric 4x4 matrices, then I get 2 quadratic surfaces, such as these ellipsoids here. What can we say about them? Well, 2 quadratic surfaces intersect in a curve of genus 1 and degree 4. It's a realization of an elliptic curve, and of course, elliptic curves are very important in applied algebraic geometry, thanks to their role in cryptography. Now, moving on, what about if we take more quadrics? We take symmetric matrices that are even larger. So maybe we take 5x5 symmetric matrices or 6x6 symmetric matrices, and we intersect the corresponding quadratic hypersurfaces. Well, if we intersect 3 quadrics in P4, then we get also a curve, a canonical curve of genus 5. And then for quadrics in P5, we get a K3 surface. So these are very interesting objects from the point of view of algebraic geometry. Now, in applied math, our algebraic geometry very often is classical 19th century algebraic geometry. So here's a pointer to Schubert's book on the calculus of enumerative geometry from 1879. And Schubert asked the following question: how many quadratic surfaces are tangent to 9 quadratic surfaces in 3 space? So let's say you spread out 9 quadratic surfaces in 3 space. European soccer balls, American footballs, we saw lots of them on the weekend. So 9 of those sprinkled all over 3 space. And then you ask the question, how many complex quadratic surfaces are tangent to the 9 given surfaces. And the answer is 666,841,088. That was derived by Schubert. And this is the actual text from Schubert's book. So he gives a little derivation. He applies the binomial, the trinomial theorem. Und so erhält man schließlich, eventually we get this number, 666 million. Now going one dimension, the analogous number for quadrics in the plane is 3,264. And this is a reference to an article that we published with Sascha Timme and Paul Breiding called 3,264 conics in a second. It appeared exactly 1 year ago in the notices of the American Math Society. And the cover picture is basically the picture that describes the math, except the artist added the galaxy to it, which I think looks nice. So here's the setting. We're given 5 conics in the plane, 5 blue quadratic surfaces, 5 real symmetric 3x3 matrices in blue. And we're interested in all red conics, having an unknown red symmetric 3x3 matrix. And the constraint is that the red conic should be tangent to each of the 5 given blue conics. There are 5 conics here. In this real guy's 4 ellipses and 1 hyperbola. Now, even earlier than Schubert, Jakob Steiner asked in 1848, how many conics are tangent to 5 given conics? And the answer, 3,264, really was a driver for parts of algebraic geometry in the late 19th and much of the 20th century. It led to numerative geometry and intersection theory. Now, in our article, we ask, in some sense, harder question. I mean, which conics are tangent to your 5 conics? Suppose you, yourself, or your niece or nephew on the weekend, you have a niece or nephew in high school, they have 5 blue conics, and they're interested in what are the red conics tangent to their 5 conics. And you can calculate the answer, hopefully in 1 second, by going to this website. So there's a software package called homotopy continuation, coded in Julia. So Julia is a numerical programming environment. So simplest way of introducing this is saying that old people use MATLAB, young people use Julia. So if you're young, you go there. And this website is just an interface where you can enter 5 conics, click a button, and then the answer comes back in hopefully 1 second. 3,264. Please interrupt with questions. I cannot see them, but if you maybe type them into the chat box, then Kathlén will read them. Now, I made the connection to data science by highlighting an optimization problem, semi-definite programming, and a statistical inference problem, maximum likelihood estimation. So again, recap, in semi-definite programming, we're maximizing or minimizing a linear functional over a yellow spectrahedron. And the boundary, at somewhere in the boundary, the optimum will be attained. In MLE, in maximum likelihood estimation, the optimal point will be in the interior of the yellow spectrahedron. And we're optimizing this function that in addition to the trace term has log det. Now the data that specify an optimization problem often are rational. So we're given the linear space L by a basis or constraints, and those constraints have rational number coefficients. The cost function S, which in statistics plays the role of the sample covariance matrix, can also be assumed to have rational entries. I should maybe say a floating point number is a rational number. Right? So a floating point approximation to a real number is a rational number. So what we input into our MATLAB or Julia system are rational numbers. Now then there's a true optimal solution for that input. And for these kind of problems, the true optimal solution has coordinates that are algebraic. They are real numbers, but they're actually real algebraic numbers. They are zeros of a polynomial with rational coefficients in one variable. And a real algebraic number has an intrinsic complexity known as degree. So it's the degree of the field extension given by those coordinates over the rational numbers. So this is the intrinsic algebraic complexity of writing down the optimal solution, irrespective of any algorithm that computes it. So,
and there is a short question in the chats before we get to the degrees. Spirosen asks, what do the vertices of the yellow tetrahedron correspond to?
Okay, very good question. So in this three-dimensional space, every point is a symmetric 3x3 matrix. On the surface, on this yellow-red cubic surface, the rank drops to 2. But then there are 4 special points, namely the vertices of our spectrahedron, where the rank drops to 1. So these singular points are the special 3x3 matrices in this family where the rank drops to 1. And that is significant because in the applications in engineering or computer science, the action is for low rank solution. So geometers who see this for the first time, they tend to think that going north is the way to go, that a smooth optimal point, the northernmost yellow point, is desirable. That's rank 2, but actually going east is the way to go. These rank 1 solutions are the ones that are most interesting in applications. So the more singular we are on this surface, the more desirable we are as an optimal solution. Okay, so we have the familiar notion of Turing complexity that you learn in your course in computer science. But in addition, from an algebraic point of view, there's an alternative measure of complexity that pertains to the intrinsic algebraic complexity of the true optimal solution, and that is the algebraic degree. Which brings me to LSSM. So LSSM is actually a project concerning linear spaces of symmetric matrices. And I got to this through work of Mateusz Michalek with Leonid Monin and Wisniewski, and in the meantime, other collaborators. And they wrote a wonderful paper called Maximum Likelihood Degree, Complete Quadrics, and a C-star Action. This is about to appear in our favorite journal. A favorite journal is called the SIAM, Journal of Applied Algebra and Geometry. And they made significant progress on the computation of these algebraic degrees. There was a number of conjectures out about them, and they solved this. So this was exciting. But of course, this appeared on the archive in April 20. Well, that's just right after the lockdown. So we all went into lockdown mode in March and in April, and our life changed. And so I took this as an idea to kind of circulate a list of questions to sort of get us together around this theme. So in May 2020, I circulated a problem list aimed at students and postdocs centered around the institute in Leipzig, but welcome to everybody, called 3,264 questions on symmetric matrices. By the way, the algebraic degree of the maximum likelihood problem will be in a moment, will be this boldface row, first row in the triangle of mysterious numbers that we saw in the beginning. Now, what happened next is that this led to a working group. So this became a collaboration project at Leipzig and worldwide with a green logo, here in black, the bell-shaped curve to highlight the connection to statistics. There was a call for papers, and they had a deadline. So by the end of November, many wonderful papers got submitted, and these 4 terrific people are putting together a special volume for the Italian math journal Le Matematiche. And so this is the LSSM issue. I myself, I'm involved in 3 articles that were submitted with mostly student co-authors, student and postdocs. So these are 3 contributions that I proposed. So in September, we posted an article Pencils of Quadrics, Old and New, with Claudia and Jelena, both students. And then in October, there was Jordan Algebras of Symmetric Matrices. Arthur is a postdoc. Henrik is a student with a numerics background. And finally, there's a paper with Taylor as a postdoc and Claudia again called Tangent Quadrics in Real 3 Space. So in this last article, let me use this as an excuse to talk about the diagram. So the diagram tells us about tangency conditions for quadratic surfaces in 3 space. So in the original thing at the beginning, we had a configuration of 9 figures in 3 space. And now these figures can be either points, lines, or planes. So in blue, we have 3 given blue points, 3 given black lines, and 3 given blue planes. And we seek the number of quadratic surfaces that are tangent to these figures. That is to say, passing through the blue points, tangent to the lines, and tangent to the planes. And the number of solutions to this problem is 104. Now, if we change this a little bit, if we take 5 lines, 2 planes, and 2 points, then there are 128 surfaces. So this is a modified, simpler version to Schubert's question with the 666 million. And the idea is let's solve those first, hopefully in under a second. Now here's the version where we do allow some conics. So delta is the number of conics. So here's the tangency to, I guess, 5 lines, 1 conic, 1 plane, and 2 points. We get this triangle. So this is the triangle of counts, algebraic degrees for this problem. And here we're studying real solutions. So what I'd like to do in the next maybe 15 minutes is to tell you about the 2 red papers, Pencils of Quadrics, and then later Jordan Algebras. But more important than perhaps our contribution is really this group project. There are lots of wonderful articles on the archive, and hopefully this will all then be in a volume by the end of the year or next year. Okay, so after this warm-up, let's jump right in. So LSSM Basics, let me give you some definitions. So if I have a subspace L in the ambient space of real symmetric n by n matrices, I'm going to say such a subspace a pencil if M is 2. So this is a 2-dimensional vector subspace or line in the appropriate projective space. Now, if M is 3, if we have a plane in the projective space of symmetric matrix, we call that a net. M is 4, we call this a web, and so on. Now, such a subspace is a point in the Grassmannian. So we have the Grassmannian of m-dimensional vector subspaces inside this ambient n+1 choose 2-dimensional space. So the Grassmannian is a manifold, the projective variety, its points are the linear spaces L. In the following discussion, I will restrict myself to a regular subspaces. And by a regular subspace, I will mean one that contains at least 1 invertible matrices. So the set of invertible matrices in the subspace is non-empty and hence dense. So a random matrix in the subspace should have non-zero determinant. If that is so, we can define the reciprocal variety, which is the inverse, L inverse. So what we do is we take any matrix in the subspace that's invertible, we invert it, right? That's a set of full rank matrices, and then we take the closure is in Sn. In a setting like this, the closure is the familiar closure you know from your first undergrad analysis course or topology course, but it agrees with the Zariski closure that you're familiar with from an algebraic geometry course. We work in a projective space, so L inverse is now a non-linear projective variety inside the n+1 choose 2 -1 dimensional projective space. So for pencil, we get a curve, for a net, we get a surface, and so on. So we're going to be interested in the basic invariance of such reciprocal linear spaces, such as the degree or maybe defining polynomials. Now, bearing the connection to statistics in mind, L inverse really is a statistical model, right? So we have covariance matrices, but then there's also the inverse to the covariance matrix of the Gaussian distribution. That's the concentration matrix. And really what we're talking about here is linear conditions, either on the covariance matrix or linear conditions on the concentration matrix. And these are the objects where we would be studying here from a statistical point of view. We're going to say the ML degree or maximum likelihood degree is the number of complex critical points of the likelihood function on the linear space L. The likelihood function is log det minus the inner product against the sample covariance matrix. Now, if we put the linear constraints on the inverse, we get the reciprocal ML degree, RMLD, again, the number of complex critical points of the log likelihood function for Gaussian models that have linear constraints on the concentration model. So this is the true intrinsic algebraic complexity of any of the coordinates of the true optimal solution, irrespective of what method you use to compute or approximate the solution to this optimization problem. Now, if S, the sample covariance matrix, is a generic matrix, sufficiently general, then this is independent. These numbers are independent of the choice of S. Furthermore, we have a natural congruence action on symmetric matrices just by change of coordinates on the quadrics we saw in our pictures. And then our first theorem is that the degree of the reciprocal variety is an upper bound on the maximum likelihood degree, and equality holds for generic subspaces. So this holds in general. And for m equals 4, these are the first row in Schubert's triangle from 1870. So this is the number of quadratic surfaces tangent to a bunch of planes and passing through a bunch of points. So here in the first row, where we have 1, 3, 9, 17, 21, and so on, we're stipulating containing a point and being tangent to a plane. Now, focusing on pencils, m equals 2, this is a well-studied situation. And so in our article, we are both reviewing classical material, and we have a few new things. So the Segre symbol, sigma, of a pencil is a multiset of partitions whose parts add up to n in total. Okay, so a partition of an integer is just an unordered collections of smaller integers that add to that integer, positive integers, and a multiset is an unordered set of such things. So how is this defined? Well, suppose you pick a basis, AB, for our two-dimensional space of symmetric matrices, and let's assume that B is invertible. Then we can look at AB inverse. Now, here's the bad news. If you multiply two symmetric matrices, the product in general is not a symmetric matrix, but it's still a square matrix, and as such, it has a Jordan canonical form. Now, the Jordan canonical form has the eigenvalues on the diagonal, and occasionally it has a 1 above the diagonal, and otherwise it's all 0. Right? So these are the Jordan blocks, and this gives a partition. So each fixed eigenvalue of this square matrix gives a partition. And then as we range over the eigenvalues, we get a multiset of partitions, and that multiset of partitions is called the Segre symbol of the pencil. It's independent of the choice of basis. So a classical theorem going back over 100 years due to Weierstrass and Segre said that these are our fundamental invariants. So two pencils are equal up to congruence. They define the same object geometrically, if and only if their Segre symbols agree, and their determinants define the same multiset of endpoints on the line. So the determinant of L is a binary form, defines a bunch of points on the projective line, and that also has to be the same. Now, interestingly, Cayley already in 1855 studied Segre symbols for essentially this purpose, namely as invariants of pairs of symmetric matrices. And he found a generating function for the number of Segre symbols. It's defined as follows. So let's say pk is the number of partitions of the positive integer k. Then you write down this infinite product. For technical reasons, we have to subtract the sum of all powers of x, and then you get the generating function for the number of Segre symbols. So there are 5 Segre symbols for n equals 3. There are 13 Segre symbols for n equals 4, and so on. So the 5 Segre symbols for n equals 3 are these symbols, right? So we either at the top here, we have a multiset of 3 trivial partitions, where each partition is simply the trivial partition of the integer 1. Further down, we have a multiset of 2 partitions, 2 trivial partitions of 2 and 1. Here we have, over there, we have a partition of 2 parts, namely the partition of 1 and the partition 1 plus 1 equals 2. And finally, here at the bottom, we have a multiset consisting of a single partition of the integer 3. Now, each of these describes a locus of pencils. And here's a bit of a geometric discussion of these pencils, right? So, well, there are different ways to think about this. Well, we can think about A. So if the matrix A is blue, it defines a conics in the plane. If the matrix B is green, it defines an ellipse in green in the plane, and they meet in 4 points. Any 2 conics in the plane meet in 4 red points. Now, the nature of these 4 8 points has to do with which Segre symbol we're in. And so here's a census. So there are 5 Segre symbols. These are now strata in the just Grassmannian G26. So we have 2-dimensional vector subspaces. Our LSSM is a 2-dimensional vector subspace in the 6-dimensional space of symmetric 3x3 matrices. This lives in P14 under the Plücker embedding. And the strata corresponding to these Segre symbols, well, the dense stratum is the 1, 1, 1. So these are pencils where A, B inverse has distinct eigenvalues. Then codimension 1, there's a double eigenvalue and a single eigenvalue, and the double eigenvalue part is non-diagonalizable. Down here, it's diagonalizable. Then 3 says there's just one eigenvalue, a triple eigenvalue. That's a codimension 2 stratum. And then down here, we have the 2, 1 case. There's a single eigenvalue, but 2 Jordan blocks. Now degrees, this is the 3 degrees I mentioned, the degree of the reciprocal curve, the ML degree, and the reciprocal ML degree. Here are representatives, and then the 4 points look like this. So if we're at the top here, we have 4 distinct points. 1 down, there's a double point and 2 others. Then here in codimension 2, one of the red, we have a triple red point and 1 other point, or 2 double points, and then all the way down, the 4 points all collide. So in general, we have the following theorem about the reciprocal curve. So if sigma is the Segre symbol, so it's a multiset of R partitions, then the reciprocal curve is a rational normal curve of degree D, where D is the sum of the first parts in each partition minus 1. The ideal is generated by a certain number of linear forms and a certain number, D choose 2, of quadrics in the unknown entries of a symmetric matrix. And here's an example. So here are for our representatives for these 5 classes. Here's simply the ideal of the reciprocal curve. So for example, if the matrix has distinct eigenvalues and hence is diagonalizable, then the reciprocal curve is a plane conic. Moving up.
And there is another question about this case. Kashkali asks if the codimensions of these loci get preserved when looking at real pencils.
That's a very good question. I believe the answer is yes. So the way the theory is set up, so there's of course real symmetric matrices behave quite differently from complex symmetric matrices. But the way this is set up is that the way this is formulated here, complex should agree with real, and it mirrors sort of the real situation that we're familiar with. So I think the answer is yes, but I have to check.
There's also another question from Carlos. If you like, what are A, B, C again?
Oh, I'm sorry. So this is simply representatives. So A, B, C are real numbers. So distinct non-zero real numbers. So if A and B and C are distinct non-real numbers, then you can choose the two conics, the blue conic, for example, A x squared, B y squared, C. So after a change of basis without loss of generality, you can choose the conics like this, where A, B, and C are distinct real numbers.
Thanks.
Now moving on to our elliptic curve, right? So now here's a, let's say, an American football intersecting a smushed up European soccer ball. So now we have 13 Segre symbols. Here the diagonalizal case with 3 distinct eigenvalues at the top. And this is the poset of closure inclusions of these strata. And then in the paper, you find a discussion of the degrees. So this is the algebraic complexity of the statistics problem, and then a description of the statistics model, the L inverse. Now, of course, it's not just red points coming together. Now it's elliptic curves degenerating in interesting ways. And there's a table that discusses all 13 cases. And the next case of 5 by 5 matrices is also very interesting. That's pertains to a Del Pezzo surface of degree 5, but that's sort of left for a future project. A last theorem from this paper is an actual formula for the maximum likelihood degree. So the maximum likelihood degree is R minus 1, where R is the number of partitions in the Segre symbol, and the reverse maximum likelihood degree is the sum of the first parts plus R minus 3. Maybe I'll skip the brown stuff in the middle, but these are really calculus problems, right? I mean, so of course, many people enter statistics with math knowledge that centers around calculus. So what I'm talking about here is if you write down, so in the ML degree case, here we're talking about a function in 2 variables, x and y, and we want to count the number of critical points of such a function. And then the reciprocal case, it's this kind of function, right? So this is really calculus in 2 variables. We're counting the number of critical points. That's it. That was the first talk. Now I'd like to talk about the other paper. So if the last 7 minutes were incomprehensible, now is the moment to reboot, and the talk will be over in 6 to 7 minutes. Now the question I'd like to address is how to multiply symmetric matrices. Well, we said a couple of minutes ago that if you multiply 2 symmetric matrices, sadly, the product is not symmetric. Wouldn't it be nice to multiply symmetric matrices and get a symmetric matrix back? And yes, you can do this. So here's a way to do this. Let's fix a invertible symmetric matrix U. I call it U for unit. And then we define an algebra structure on the space of symmetric matrix by saying that the U product of 2 symmetric matrices A and Y is the average of x u inverse y and y u inverse x. Right? Because it's an average, this is now a symmetric matrix, right? So this is a way of multiplying symmetric matrices x and y and getting a symmetric matrix. Now, if U is clear from context, I'm going to drop the subscript in the bullet, and the bullet product is bilinear, it's commutative, and the unit is U. In fact, if we take U to be the identity matrix, it's simply the average of x, y, and yx. Now, this is a very good structure, right? This is a very good commutative algebra structure. However, associativity fails. So this is a natural situation where you have a commutative algebra that is not quite associative. However, there is an almost associativity, namely the following holds. X bullet x times x bullet y is always equal to x bullet x bullet y. Now this is an axiom for what is known as a Jordan algebra. Now, when I got into this, I did not know about Jordan algebras. I knew Lie algebra. So at Lie algebras, we know there's sort of, if you know skew-symmetric matrices, you know Lie algebras. But somehow I never had heard about Jordan algebra. So who cares, right? Why is this interesting? That's a typo. That should be a question. Q. Who cares? Well, people care, right? People in physics, statistics, and optimization care. In fact, the structure of a Jordan algebra was first proposed in 1938 in this paper by Jordan, Van Neumann, and Wegener, and an algebraic generalization of the quantum mechanical formalism. So when the foundations of quantum mechanics, the mathematical foundations where quantum mechanics were formulated, Jordan algebras were proposed, and they continue to be of interest in this context. Statisticians got on board in the 1980s, right? So as we discussed, we're imposing linear constraints on both the covariance and the inverse convariance matrix, and Jensen published in 1988 this article in the Annals of Statistics. But also, this is of considerable interest in semi-definite programming as a tool for dimension reduction. So here's an article by Permenter and Pablo Perillo that was published last year, Dimension Reduction for Semi-Definite Programs via Jordan algebras. So these things are relevant. Well, how so? Well, we have the following theorem. Suppose you have an LSSM, L, and let's fix our unit to be an invertible matrix in this linear space. Then the following three conditions are equivalent. A, the reciprocal variety is again a linear space. So we have linear constraints on the covariance matrix, and then dually interpreted, they are linear again on the concentration matrix. Second condition is L is a subalgebra of the Jordan algebra. So Sn is the Jordan algebra of symmetric matrices, n by n symmetric matrices with unit U. And once we know that L inverse is linear again, it's actually the case that L and L inverse are essentially the same up to this shift, right? So once L satisfies the Jordan algebra property, we obtain L inverse from L by this operation. Here's a little example. So let's say M and N are both 4. So here is a 4-dimensional LSSM, right? So if X, Y, Z, and W vary over all real numbers, then this gives us an LSSM on the left. On the right, we get a different LSSM. One of these is a Jordan algebra and the other one isn't. And it's a little exercise. So it turns out the right one is a Jordan algebra. So the set of all matrix inverses of all these matrices is a projective threefold that's just flat, linear space. And here it's highly nonlinear. So they look very similar. I'm just changing the sign on this one entry. And I go from a nonlinear threefold to linear threefold. I promised to be done in time. I am done in time. So let me wrap up by admitting that my problem list, the one that was circulated last May, did not have 3,264 questions. I ran out of steam after 65. It only had 65 questions. In the meantime, many of these were addressed and answered. But there are questions out there, right? There's still 3,199 questions out there for you to find, to work on, and to solve. Thank you very much for your attention.
Yeah, thanks a lot, Bernd. I will clap for all the many participants that we have. So there is directly a question by Rosa in the chat, which is, I guess, exactly related to the last theorem you showed us, which is the equivalence supposed to be conjugation, or is it really U inverse twice?
It's actually U inverse twice, but remember that U is a symmetric matrix.
So yeah, so it's like the same. It is actually a conjugation.
In this case, so U is in L, and this is a symmetric matrix.
Yes, so now we welcome more questions. If you have a more complicated question, I'm also happy to unmute you and allow you to talk. Or you're also welcome to write in the chat, whatever is more convenient. If someone wants to.
As always in the calculus class, if you don't have questions for me, I have questions for you. For example, what's the relationship between this blue picture and these matrices?
Should I now randomly unmute someone?
I'm waiting for questions. So if nobody has a question.
I have a question otherwise. Going back to these SAGA symbols. So you said, so there is, we may have two questions in some sense. One question is maybe a literature question, which Peter Bürgerser, who also is here, was here at least, asked me just the other day, namely, what is a good reference to learn about SAGA symbols?
That's a very good question. So I learned about this from an unpublished manuscript by Peter Bellmans. So that's actually cited. It's sort of hidden. And there's maybe one good reference is the book by Gantmacher. So Gantmacher has this famous book on matrix theory and linear algebra. And in the background, there's a sort of Kronecker Weierstrass theorem of matrix pencils. So I would say, from a general linear algebra point of view, and perhaps Kaj can comment on that, Gantmacher's book is a very good general reference. But it's not very geometric. So the connection to projective geometry and these kind of geometric discussions, I did not find a super good reference. It's mentioned very briefly in Dolgachev's book on classical algebraic geometry, but quite brief. So
does he also call them SAGA symbols there, Dolgachev?
And slightly self-serving, I would recommend our paper.
Yes, of course. Because that brings me, before I ask the other questions that are in the chat, that brings me to the related question. In your paper, you was focusing on SAGA symbols of these regular pencils, but of course, it's also very interesting to study singular pencils, so pencils that are completely determined in the terminal locus.
I completely agree. Yeah. So in our paper, we decided to ignore them. So we decided,
which makes sense from the statistics point of view.
From this point of view, we were focused on regular pencils, but you're absolutely right. Singular pencils are important also in the applications. But in our paper, we said, let's understand the regular pencils first.
Yes, exactly. So, but yeah. Anyhow. Yes, then there is a question in the chat by Ragnar Friholanti. I'm not sure to which slide it is. He says, I'm confused. How does... this is, I think, about the last theorem again that you showed us. How does point A in the theorem on this slide depend on U?
Okay, very good question. It's actually independent of U, provided U is in L. So once it's true for one, if you pick one U in L that's invertible, then it will be true for every other U in L. So a posteriori, so the definition here is, it looks like it depends on U, but a posteriori, it's independent of U.
I hope that maybe we can also move on.
You can see this formula. It's kind of interesting here, right? So you just play around this, we do this with one U and you have a different U, you actually get the same L inverse. Carlos raised hand, it says.
Yes, let's move on soon to the, maybe one more question and then move on to the informal part where we also then unmute everyone who raises hands. But there's one more question, which is from Jared Miller. How to build or read these Schubert triangles? Is this a table of numbers of tangent quadrics? What are the settings, points, line, planes of the numbers in the triangle?
So how do you make the triangle? This is a very, very good question. So I tell you my admission. I actually computed this in Macaulay too, right? So when I first got into this, I wanted to do it myself, right? And so I set up a sequence of problems, and each of these numbers counts the number of solutions to a system of polynomial equations. and the numbers are small enough so that I was able to make this triangle in Macaulay too. Now, the bigger triangles you have to use, so we found it's harder, we use numerical methods. But of course, after we understood this, we can actually go to Schubert, and Schubert knew this, right? So if you read the fine print, so we're in a slight advantage here of being able to read in German, right? So you look at die rechts auftretende Symbole and so on. Actually, it's all in Schubert, right? So you can make these triangles by really reading Schubert carefully. So I think there are three answers. So either you use symbolic computing, such as Macaulay 2, or use numerical computing, such as Bertini or homotopy continuation, or you actually read Schubert's book.
Yeah, thanks. Let's maybe move on to the informal discussion, where we can maybe have more questions also in oral style, when if we want to discuss more, if you have a little bit of more time for us, Bernd.
Sure.
So I just sent in the chat, like, everybody who wants to stick around for the informal discussion, just raise your hand, and then we will promote you to panelist. But before that, we thank Bernd one more time and stop the recording of this webinar.